This series will present the content of the course CIV8530, Structural and System Reliability. I'm James Goulet, professor at Polytechnique Montreal. So in this first module, we're going to look at the introduction of the course. So, and more specifically, we're going to look at an introduction about what is reliability, what are the notion of risk, what is the study plan, and finally, we're going to break down every topic we're going to cover in the context of the course. So you can see here an outline. We're going to see it point by point in the last section. So first, in the introduction, what are the basic concepts associated with reliability? What are the common pitfalls that we can encounter when thinking about reliability analysis? And why would one need to do a reliability analysis? So first, in terms of terminology, we're going to break it down. What is a component? A component is going to be a single element considered as indivisible, cannot be further split down into smaller elements. So imagine a truss, one element, one bar in a truss would be a component. Then we have a system. A system is the assembly of multiple components. So you can imagine that little bridge here, each element, so each component would be assembled to make a larger, more complex system. In reliability, when we talk about the state of a system, we're going to say it's either surviving or failing. Okay, these are going to be the only two states we're going to be considering. And we want to compute in reliability the probability of failure. So the failure is considered not only as a collapse or something catastrophic like this, but it's simply the domain where the structure, the component, or the system is not fulfilling its purpose. So it can be either with respect to limit states, so that are associated with safety, or also serviceability. The reliability is defined as the uh, probability of survival. Okay, but in reliability, typically what we're going to compute is not the probability of survival, it's going to be the probability of failure. Okay, which is the probability of survival is going to be 1 minus PF, probability of failure. So why do we compute probability of failure rather than probability of survival? Typically, probability of failure are going to be small and are going to be easy to express, whereas probability of survival is going to be 99.999. So it's harder to take care than 10 to the minus 6 or 10 to the minus 5 or something like this. So whenever you're going to see PF, it's going to refer to the probability of failure, F for failure. Okay, so let's look at that probability of failure. Let's consider one component. So we have a bar subject to a tensile force S that has a strength or resistance R. Okay, we're going to express both this capacity and demand on our axis here, expressed in kilonewtons. So first I'm going to say, okay, I have a nominal resistance of, say, close to 20 kilonewtons. I have a solicitation that's probably around 12 kilonewtons. So in that case, since the solicitation is less than the resistance, I can say that that bar is strong enough. But in practice, when we design such a bar, what we're going to do is that we're going to use coefficient that's going to bring down the nominal resistance by a factor that is less than 1. That's going to be multiplied by that resistance. And I'm going to do the same thing for the solicitation. I'm going to use a coefficient that is larger than 1 to increase the solicitation. And if these weighted value for solicitation resistance tells me that the weighted resistance is still larger than the weighted solicitation, all is good. My design is safe. And we use these coefficients to have a safety margin or to have some conservatism in our design scope. But what happened in the case where you do these conservative analysis and you realize that your weighted down resistance is less than the weighted solicitation? In that case, you cannot justify the safety of your design or of an existing component with such conservative practices. So it's when you want to go deeper and use reliability. But in that case, you need to model your resistance not as a deterministic value, but as a whole distribution. Okay, that whole distribution, we're going to come back to this in the later module, but for now, I'm just going to tell you this is a probability density function that represents the the possible value for, or the relative plausibility of all the possible value for the resistance, where here we would have the mean resistance, okay, and all the possible variability around that mean. We have the same thing for the solicitation. And I'm pretty sure if you've come into contact with reliability content in some civil engineering manual, you might have seen often that this is represented as the probability of failure. But be careful, this is not. Okay, the intersection between these two curves doesn't correspond to the probability of failure. This is wrongfully represented in many manual. If we want to think about reliability and or probability of failure, we need to look at it in a multivariate domain. Okay, here we have two times kind of the same information. On one axis, we have the resistance, the other we have solicitation. So here we have a 2D surface representing a joint PDF. Here it's simply a contour plot. And we need to look at the problem in such multivariate domain if we want to compute the probability of failure. But be careful, before going there in detail, we need to see some background concepts. So first, we're going to do a revision of linear algebra and probability theory. We're going to look at module 1 about what are the probability distributions, so univariate probability distribution. Then we're going to see how to formulate reliability problem in such a way. We're going to cover this in module 2. And finally, module 3, we're going to see how from knowledge about univariate probability density, we can build such multivariate probability density in an arbitrary number of dimensions to suit our structural and system reliability problems. Okay, now, why would we be interested in structural reliability problem? But the reliability is a measure of a system to measure the capacity of a system to fulfill its function, whether it is safety or serviceability issue. And this is given our knowledge of this one. So what does it mean? It means that the reliability represents a reflection of our knowledge of the system and not the system itself. So what does this imply? It implies that if I give someone a task to come up with reliability analysis for a structure, he or she's gonna obtain a given reliability index or probability of failure that are associated with his level of knowledge of the structure and the hypothesis he takes along the way in his analysis. If I task someone else to do the same analysis, depending on his or her knowledge of the structure, he might come up with a different probability of failure. So it's really a representation of our knowledge of the structure, and as knowledge can evolve through time with the accumulation of information, as I'm going to have new information or observation available to characterize all the variable involved in my analysis, that probability of failure is going to evolve in time as well. So the goal of obtaining such probability of failure is to identify whether or not the risk that is entailed with my structure is acceptable or not. Where we're going to say that the risks are going to be the consequence of a failure weighted by its probability of occurrence. So now let's dig a little deeper into the notion of risk. So we're going to cover in this subsection the relation between risk and reliability. We're going to say, okay, how do we quantify risk on an individual level? How do we quantify risk in a societal level? And for a civil engineering perspective, a structural engineering perspective, what are the target reliability indices that are prescribed in codes? And finally, in codes, all these coefficients that are there to weight the loading components or the resistance components, where do they come from and why do we use such coefficients? So first, when talking about risk, so we can see that here we can see that risk could be unacceptable, that cannot be justified in any circumstances. We can have a risk that could be tolerated if the cost of lowering the risk is disproportionate compared to the consequences, and we could have a negligible risk where the situation doesn't require modifying anything. But if we want to break it down further, we can look at the individual risk. So in terms of individual risk, the typical way of seeing this is the annual probability of death or harm that is caused by the event. In terms of society, risk is typically quantified by the average number of death per year. So if we look at the individual risk, so we're going to see that the individual risk is modified according to the level of personal acceptability of the task we're doing. So for instance, in this diagram, we can see here on the horizontal axis, we have the acceptability index. Okay, so on the left, we have something that is fully personal choice. On the right, it's involuntary. Okay, you didn't choose to be exposed to that risk. And keep in mind that beta is not the same as what we're going to see in reliability theory as our reliability index. It's just something specific to the notion of risk. So just don't mix up those two betas. On the vertical axis, here what we have is individual risk in terms of, say, death per year or probability of death per year. So what we're going to see here is that if you're doing, say, rock climbing, so when you're doing rock climbing, it's an activity, it's a personal choice. You choose to expose yourself to this activity. So since it's fully voluntary, you're going to accept to expose yourself to a much higher level of risk than, say, if you take a car or take a bus. Why? Because there's only a limited number of kind of uh, personal choice in having to move yourself around the city. And on the other end of the spectrum, being struck by lightning, no one will choose to expose themselves to be struck by lightning. So the level of acceptability is, or the individual risk is much higher, much lower. So whatever is below that line is going to be deemed acceptable. Whatever is above that line would be deemed unacceptable. Okay, this is for a personal risk level. Now, if we look at a societal level, so what we have here is in this table, the vertical axis is the probability of occurrence. The horizontal axis are different consequences. So whether it's number of death, the contaminated surface for water body, or the value of the failure, okay, in terms of, say, millions of dollars. So whatever we have on the top right here is going to be, this is unacceptable. Okay, we cannot allow for such a risk to occur. If we look on the bottom here, the risk is acceptable. So if you're going to tell me what we can accept having 100 people dying at the societal level, the answer is yes. Why? Because we look here at tiny probability of occurrence, okay? 10 to the minus 9 is really small. So if you look at the kind of typical lottery we have here in Quebec, 649, there's one draw every 2 weeks. So that makes 26 possibly to play per a year. And there's roughly 1 out of 14 million chances of winning. Okay, so if one would be buying one ticket every time as possible throughout the year, that would still make a probability of winning of 2 to the minus 6 per year. So that makes it a very tiny probability already. So whatever is here is really some infrequent event. Okay, so that's why we can allow such a risk, even if it involves catastrophic outcome, because their probability of occurrence is extremely low. Okay, if we're here, we don't need further thing, we can accept it. If uh, uh, and and so here we can also have a situation that's going to be acceptable if, because the consequences are low enough at the societal level. And here we need further study to say on which side of the line are we going to be. So now, what are the target reliability values for structural engineering? So typically, if we look at the values that are prescribed in codes such as the SX code for bridges, the typical probability of failure for a bridge that would be subject to regular inspection and that has a ductile failure mode is going to be 2.3 times 10 to the minus 4 per year. Okay, and that corresponds globally at a societal level to an annual death rate linked with a collapse that is roughly 10 to the minus 7 per year. Okay, so that's interesting, but how did we come up to this? Okay, how do we come up to this number? And how do we use it in practice? So in codes, you're going to see that we're not necessarily designing structures with reliability analysis. What we're doing instead is that we're using such coefficient to weight down the value associated with loading and to weight up the values associated with the resistance. But where are those coefficients coming from? Okay, they're coming from what we call LRFD, load resistant factor design, whereas before the 1990s, we were obtaining something like this. So according to, say, here's an example of different span of bridges, we would have widely diverging or widely different reliability index. So reliability index we haven't seen yet, but this is what quantify the probability of failure. So this is directly related to the probability of failure. And here what we're going to see later on is that between a 2 and a 4, it's a really wide gap in the probability of failure. So this was before LRFD. Now, after LRFD, where we introduced those weighting coefficients, now we see that depending on this example, different span of bridges, they all roughly have the same reliability index. And this is what we want. We want a uniform level of risk around all the structure we can design. So all those coefficients were calibrated to obtain a uniform level of reliability across my possible structures. Where here, that reliability index that we're going to see later on as beta is a function of the probability of failure. We're going to cover this in the later videos. So another example, this is for the value of the reliability index before using those coefficients and after using the coefficients on the vertical axis. So you see that now all these different structures are either steel, reinforced concrete, pre-stressed concrete, all have the same reliability index, whereas before, without using those coefficients, they might have widely different reliability index. Okay, so now it's really to convey the goal that these coefficients are there to obtain a uniform level of risk across the designs of my structure. And this is the same design procedure for coefficient that is used in AASHTO in the US for bridges, CSA S6 in Canada for bridges, the National Code of Buildings in Canada, ACI 318 for concrete, ACI ISC 360 for steel, and all the Euro codes. Okay, all the building codes around the world are building their coefficient around that same probability theory to obtain a uniform risk. However, that being said, it's the reliability theory is not only used to calibrate code, okay? Because there are several possible level of reliability analysis. So if we look at the level 1, we're going to just say this is what is typically prescribed by codes, okay? These coefficients that are used to weight up or weight down resistance or solicitation, okay? This current design practice. And these are typically very conservative because they're meant to be used quickly to design new structures or to evaluate kind of day-to-day existing structures. The second level is going to be a simplified probabilistic approach. This is where we're going to simply model the resistance and solicitation directly as random variables to make very simple problems. And this is typically what is used to calibrate codes. And level 3 is going to be the fully probabilistic approach. Okay, this is where we're really going to model all the variables associated with our solicitation models or resistance model explicitly by their own random variable. So It could be the Young's modulus, the resistance of the steel, the resistance of the concrete. All the variables are going to themselves be explicitly modeled by random variable. So this is much more involved analysis, but in the end, it's going to allow us to reduce the amount of conservatism and potentially justify the safety of a structure by really not leaving information on the table and not using conservative approaches such as the one in level 1 and level 2. So obviously such level 3 analysis is not going to be done for any type of everyday structure. It is going to be done for much bigger structure, whereas the cost of or the value of the structure themselves will justify the engineering time required to perform such advanced analysis, whether it is a large dam, a very intrinsically complex structure, such as here the rooftop of our Olympic Stadium. This is the Metropolitan Highway that cross Montreal, or these are the large bridges in the region of Quebec cities. So for such high values infrastructure, okay, the cost of replacing or strengthening those is so high that here, instead of using these conservative approaches, we can do an advanced analysis where we're going to take into account all the information that is available to us to really add the most accurate portrait possible about the safety and serviceability in terms of their probability of failure. But the question we're going to address in this class is how can we compute those probability of failure using either level 2 or level 3 analysis. Okay, so now let's look at the study plan for the course. Where can we find them? What is the overall goals of the class? What are going to be the evaluation? What are going to be the practical work to do? What is the documentation available? Software we're going to use? What is going to be the schedule? And some little Varia stuff. So if we start where to find a study plan, this one you can find it on Moodle. So if you go here, you're going to have the study plan available here. Then what are the goals of the class? So the first overarching goal of the class is how can we formulate reliability problems? So whether we start from a simple component, you go with a simple system or a very complex system, how can you translate your knowledge of such component or system into a reliability problem? Then once you formulate the reliability problem, how can we estimate the failure probability? We're going to see two main types of approach. So the first one is going to be associated with what I labeled here as a bulldozer. Okay, these are going to be sampling-based approach. These are approaches that are widely applicable, but can be fairly slow. On the other end, we're going to have that race car. These are going to be analytical approach that are very fast, but require that we satisfy some hypothesis in order to apply it. So we're going to see both, and we're going to see the strength and limitation of each. So this is in order to estimate the probability of failure itself. And finally, the last objective is going to be how can we have a toolbox in order to say, what do I do with my probability of failure? So if the probability of failure I compute satisfy the requirement, I'm all good. But what happens if it doesn't? How can I act upon such probability of failure? What variable should I act upon? Which variable has most influence on the probability of failure? How can I reduce the uncertainty associated with some of my variable? Okay, how can I incorporate the knowledge associated with some observation into my reliability analysis? We're going to cover all these aspects as well. So once you've computed the probability of failure, how do you act upon it? And the goal of this is to be able to understand all the theory behind what is already available in common libraries such as Pystra or Pyre, where you can compute with those Python library all the quantities associated with probability of failure. Okay, I want you to understand what is behind so that you can then safely use those existing tools, not as a black box, but as something where you understand the key theory behind. So the evaluation, we're going to have five homeworks, worth for 6% each, and they're going to be 2 exams, one midterm, and one final exam for 35% each. So practical work is going to involve really programming and implementing the key concept and the key method associated with reliability. The exam are going to be associated with understanding questions. So really, we're going to cover the theory we're seeing and to verify that you really understand the key concept, not only that you've looked at the formula and you're applying the formulas. So for the homeworks, there are going to be 5 of them. The first one is already available on Moodle. So if you look here for the homeworks, so you're going to see here the label in order to build up the team. You're going to see here a Python tutorial. If you're rusted with respect to Python programming, I've prepared a little tutorial that is to be used in VS Code. This is the self-correction policy. You can see an example of source code that is required with your submission. You can have a template in case you want to do your own work in LaTeX, but if you want to do it by hand, if you want to do it on Word, you have the freedom to choose whatever you want. If you want to use LaTeX, I've already prepared a template here for you. This is the correction grid, and the TP1 is already available here. So the homework can be done either alone or in team of 2 person. Although you can collaborate between team, I see no problem in this. You still need to submit one homework per team. You need to provide a complete solution for each of the problems. So it needs to be with such a level of detail that if I want to correct my own copy, I could use your homework. Okay, now the level of detail is sufficient for someone else to understand what you did. As I said, there's going to be a self-correction procedure that is available on Moodle. In the homeworks, as the electronic version have to be submitted at 8 p.m. the day before the course, and the corrected version has to be submitted the following week before noon. So what I suggest you to do, the easiest way of going through this class is to first read all the suggested lectures that are available in the study plan ahead of attending the class. Okay, so that when you're here, you're gonna really be able to get the high level details of what is the core that you will already have covered in those readings. Okay, all of those are available on the study plan, and all the references are either available at the bottom here or are linked to those references. And the 2 main references that we're going to use is the excellent book from Armand Karigian, Structural and System Reliability. This is building upon the course he was teaching at UC Berkeley. And if you want some more in-depth coverage about revision, so whether it is about probability theory, linear algebra, all of this, and probability distribution, you can look at my book. This one is freely available online. So for documentation and software, so as I said, all the things to read are available on the study plan. So they are listed in the study plan, available on Moodle. So all the courses video are available on YouTube in French and in English. So the slides are available online on Moodle and on my university website. The revision questions are all available on Moodle. So if you look here, if you go a little up, for each module, you're going to have a complete list of revision questions you can go through in order to prepare you for the exam. So each module has its own list of questions. Then we're going to have the software, Pyri. I've put on Moodle some link to the library here with a little tutorial video on how to use it. And in case, depending on the progression, for those attending the class in person, we might adapt the progression of the class depending on the amount of question or interaction we have in class. So for those that have questions outside the course or office hours, use the Moodle forum. So you can see we have 2 Moodle forums here. So either for kind of administrative stuff or for question related to the material of the course. So use one of these 2 forums to ask your questions. So for those in person, we're going to take some breaks. This is not applicable for online. So finally, we're going to look at the breakdown of all the topics we're going to cover in this video series for the course. So we're going to break it into 5 larger categories. So first, we're going to talk about the revision about probability theory. Then we're going to look at the core module about how can we formulate a reliability problem. Okay, this is going to be what we're going to cover in those modules. Then once we have formulated our reliability problem, how can we estimate the failure probability using sampling method? How can we estimate failure probability using analytical method? And finally, how can we use the results? So how can we build our toolbox to say, how can I act upon a reliability analysis result? Okay, what variable should I act upon and in what way? So the content of this course might take you out of your comfort zone, but we're really going to go step by step and we're going to review all the concept along the way so that we can really extend this zone so that you're going to be able to master all the concept associated with probability theory and you're going to be able to understand what is behind the libraries such as Pyre or Pistra so that you can use reliability concept to evaluate what is the probability of failure in order to quantify the risk encountered by large-scale infrastructure. So first thing we're going to do is to do a review of key concepts associated with linear algebra as well as probability theory. So concept of linear algebra, for probability theory, what is an event, what is an ensemble, what is a random variable, what is a probability density, what is an expected value, Bayes theorem, function of random variables. Okay, we're going to review all this because we're going to reuse these concepts in the following module. In module 1, we're going to cover what are the basic probability densities or law of probabilities for random variables that are going to be used in the context of reliability. So probability law will describe in the context of reliability most often a probability density function that represents what is the relative plausibility of obtaining different values for a physical phenomenon. And those we're going to cover here for the context of reliability theory are the normal distribution or Gaussian, log normal, the gamma, the Gumbel, and the beta. And we can see here an example of either marginal or multivariate probability density function for, in this case, a log normal distribution. We're going to see all of them in module 1. Module 2, we're really going to tackle how do we formulate reliability problem. And we're going to see it in 2 ways. Either for the special case, we're going to formulate it directly with the resistance and solicitation considered as random variable themselves, or the general case, which is the much stronger one, where we're going to define what we're going to call a limit state function that involves breaking down the strength, the solicitation, the resistance and solicitation into all their individual variables involved into them. And at the end, we're going to see that estimating a failure probability at the end boils down to performing an integration in a multivariate domain. But in most cases, there's no exact closed form solution to those integrals. So in this course, we're never going to integrate analytically as you've done in your calculus class, okay? Because we have no solution to this integral. What we're going to see instead is both analytical and numerical methods in order to obtain estimation of the result of those integral. That's going to lead to our probability of failure. So before going there, module 3, we're going to see how, from the knowledge about univariate probability density function, we can build multivariate probability density function. So we are going to see this through 2 methods, either the Morgenstern method or the Nassif method. Module 4, or first model where we're going to estimate probability of failure. And we're going to do so using the sampling method called Monte Carlo. So as I said, estimating the probability of failure boils down to making or estimating an integral in a large multivariate space. So we're going to see in that module how in a from a general standpoint, Monte Carlo integration works and how can we apply it to reliability. And then we're going to see what are the limitations associated with that method. And as I alluded to earlier, so Monte Carlo sampling can be seen as a bulldozer. It can go everywhere, but it will go slowly. So when I say slowly, it's because it's gonna consume a lot of computing resources in order to be applied. Module 5, we're going to see our two first analytical methods to evaluate the probability of failure, namely MCFOSM and FOSM. So mean-centered first order second moment and first order second moment. So these could be seen as a kind of old race car, meaning that they were state of the art many years ago. They're not necessarily anymore, but they're much faster than the sampling-based method. So the essence of it, how can we see it? We can see here a probability density function for two variable one u1 and u2. So this is going to be the probability of occurrence of the variable involved in our reliability analysis. And what we have here in magenta is our limit state function, the boundary that separate our failure domain from our survival domain. And what we want to do with those methods, these first order methods, we're going to linearize that limit, that boundary, and that's going to accelerate the computation. Okay. But why are we seeing a method that is not deemed as state of the art? Is because these basic methods are behind all the more advanced methods we're going to see next. Okay, so it's really important to understand those to see where the most accurate method come from. With those two methods, we assume that we only know the mean and variances associated with our random variable. We're not really going to consider their entire distribution. And that's why these are not anymore state of the art. So something that is better, that is more recent, is going to be form. Form is called first order reliability method. And now, contrarily to what we have with FOSM, we're going to consider explicitly our knowledge about the probability density for each quantity involved. Module 7, we're going to see our first tool. So how can we perform sensitivity analysis using the analysis we've already performed, say, with form? So we want to know what is the relative importance of each random variable in my reliability analysis. Then we're going to see here how are coefficients available in codes, either to weight up the solicitation or weight down the resistance, are defined in construction codes. Okay, so how are these alpha, gamma, psi, and phi calibrated? And finally, we're going to see that what happens if random variables are themselves parameterized by some variables? How can we define the relative importance of each of those, what we're going to call hyperparameters? So how does all of these, say, mean values and standard deviation, which one is affecting most my probability of failure? And the thing is that with all these three things, we're going to see that we are going to have directly access to ways of quantifying those three things using forms analysis we'll have already performed. Module 8, we're going to see a more advanced analytical method to perform the estimation of probability of failure, namely SORM, second order reliability method. So we saw earlier that with form or FOSM, we were linearizing or replacing by a plane or hyperplane or limit state function. Now what we're going to do is that we're going to replace what was a plane by a parabola. So we're going to be able to increase our level of accuracy while maintaining a method that is very fast. So SORM, second order reliability method. Module 9, we're going to extend everything we've done so far that would have been for component. We're going to extend it for systems. So we're going to see how can we formulate system reliability problem compared to what we were doing previously for component reliability problem. And then how can we estimate such probability of failure? So we're going to see how to formulate it, how to apply a form type solution to system reliability problem, and how can we apply sampling-based method for system reliability problem. So an example here, we can see a bridge that would have multiple beam how can we compute the reliability of such a system that is made of multiple beams, where either we can have a system in parallel or in series. So each span is a parallel system because all the beams needs to fail if we want to have the collapse of this structure. But then each different span could be seen as a series system because if any of those fail, we're going to have a failure. Okay, so we are going to see that systems can be represented as a mix of series component and parallel component, and how can we assemble them together to estimate the system failure probability. Module 10, we're going to cover the uncertainty analysis. So what happens if we have uncertainty about the hyperparameter associated with, say, the mean for the solicitation, so the mean for S and the standard deviation for S? What if those are uncertain? How does this have an impact on my probability of failure? Okay, so how can we analyze the values associated with a graph such as this one? Module 1, we're going to see how can we act upon our knowledge using observation. So how can we reduce the uncertainties associated with my variables involved in my reliability analysis from empirical observations. So for this, we're going to see what are the types and source of uncertainties, what are the types of observations or information I can do, and finally, how can I incorporate this knowledge from observation into the knowledge of my random variables. And we're going to do this through Bayesian estimation theory. And we're going to see that this process change whether we're in the conception phase, so design phase, or analysis phase. Okay, because this modify my access to information. And this is associated with what we're going to cover later on, the nature of uncertainty that is either aleatory or epistemic. Module 12, we're going to see more advanced sampling techniques. So the first one was the plain Monte Carlo, was like our bulldozer, but we're going to see a more advanced one, which is still consuming in terms of computational resources, but much less than the crude Monte Carlo. So that's going to allow us to perform still methods that are widely applicable, but that are more efficient than the basic one we're going to see that are very simple at the beginning. Finally, module 13, and we're going to look at how can we take decision following a reliability analysis. For instance, for all these very important structures, if the probability of failure we compute is larger than the admissible value prescribed by codes, what should I do? Okay, I don't want to directly necessarily go and replace the structure. We want to say, for instance, do I want to replace the structure right away or do I want to wait? How do I choose between these decisions, these actions, in uncertain contexts? So to do this, we have to evaluate the risk, where the risk is going to be modeled, as I said earlier, by the consequences weighted by the probability of occurrence. And in order to choose between those two actions, we need to look at the utility theory, which is based upon maximizing what we're going to see as the expected utility. In very simple terms, we can see now the expected utility would be computing the average, say, amount of dollars given an action for the action of waiting or for the action of replacing. So if we wait, it's going to be a cost of failure times the probability of failure we compute with our reliability analysis. If we decide to replace, it's deterministic. It's going to be the cost of replacement. Okay, and with the utility theory, we're going to take the action that maximize this expectation. We're going to see in the next module in detail the notion of expectation. But this, of course, this is a very oversimplified analysis. Why? Because we need to cover more concepts. First is that $1 today is not $1 in 20 years from now. We need to have a cost actualization. And also, gaining $1 doesn't have the same utility whether I currently have $1 or whether I currently have $1,000,000. Okay, so we need to cover the concept associated with risk aversion. Okay, so we're going to cover that in detail in module 13. Finally, our last module, module 14, is going to be meta modeling or surrogate modeling. So what happens if your reliability analysis involves such a model that can take minutes, if not hours, if not days of compute time to obtain one evaluation? You're going to see that in order to perform either form analysis or apply Monte Carlo simulation, we might need tens, if not hundreds, if not thousands of run of our model. That might lead to unacceptable computational demand. So in that case, what we can do is we can build a meta model or a surrogate model, so meaning a model of a model. So a small, easily evaluated model that's going to mimic the response of our full complex, heavy finite element model. But don't get excited too quickly. We're not in the context of the courses handle such complex model because we want to keep the focus on the key concept of probability theory. So we're going to deal more with simple assembly or components such as these ones. So that covered the outline of what we have in the topic. So each of the module is going to have its own video about all this courses outline.